All right, so let's kind of pick up with where we were the other day. So we talked about using the Laplace transform for circuit analysis. And we said, I begin always with the circuits that I really have in the time domain, which basically consists of real components, real voltage sources, and I measure things in the time domain. So meaning Vn of t, might be a sine wave that's a function of time. Well, to perform analysis, we typically transform into new domains. So previously we talked about phasor analysis if we had sinusoidal inputs, and phasor analysis only applied if we had sinusoidal inputs. Well, in more general sense, I can use what we call the Laplace domain. So I can transform this circuit on the left to this one on the right, basically using the Laplace transform. So what I have in the circuit on the right is basically the Laplace transform of the input, and then these sort of impedances in the Laplace domain. And then I say the output voltage that I have here is not the actual output voltage I would have, but the Laplace transform of that output voltage. All right, so what we said was you could use this circuit and do impedance analysis just as we always have, okay? And so for this circuit, I can say I have a voltage divider, which means that V out of S is equal to V in of S times 1 over SC, so that's the impedance of the capacitor, over the total impedance, 1 over SC plus R. Now, we talked in the past about the fact that this needs to be a rational function of S, which means that it needs to be a polynomial of S. So this idea that we talked about previously is in the Laplace or S domain, these sort of transfer functions is what we called these relationships, needed to be these rational functions of S. So we have a polynomial on top, like what I have right here, and a polynomial on the bottom, okay? So basically what that means is I have, S to the power of something in all of my terms. And obviously this guy is not in that form because I have S's on the bottom. So I multiply top and bottom by SC, right? And if I do that, I'm effectively multiplying the whole thing by 1, but this becomes Vn of S times 1 over SCR plus 1. And I can write this as V out of S over V in of S, right? So I've just basically divided both sides by V in of S, and I get this result, and we sometimes call this, as we said, the transfer function. And what it does is it describes for a particular input, right? If we know the Laplace transform of, so transfer function, so what it does is it says if we know the Laplace transform of the input, the Laplace transform of the input times the transfer function gives us the Laplace transform of the output. So we write it sometimes with a picture like this. Okay, and here's V out of S like so. Okay? All right. So the other day we sort of ended with, well, we can use this for analysis and we can use a couple of different types of inputs. So let's say that in this particular case, let's say that Vn of t is a complex exponential e to the s naught t only for t greater than or equal to 0. Okay? So in general, we've said that, for the s values we have, s is a complex number, s equals sigma plus j omega. Okay? So that's the case here. All right? So what I'm going to say then is to do my analysis, I'm going to need to get the Laplace transform of that Vn. So for an exponential, so we talked about this before. If I have e to the negative at for t greater than 0, that Laplace transform of that is 1 over s plus a. So if I have e to the s naught t, that becomes 1 over s minus s naught. Okay? So we're going to use that analysis here with this RC circuit. So I go over and I say, well, V out of S equals H of S times V in of S. So in this case, my H of S is 1 over S RC plus 1 times 1 over S minus S naught. Okay? Now, to make things easy, I want to choose numbers here. So I'm going to let RC be equal to 0.1. And that's a tau value. It's a time constant value, so that would have units of seconds. All right, so what would make that happen? Well, let's say we had a pretty normal circuit. Let's say we had R equal to 1,000 ohms. So just to check that, so 10 to the third times C equals 10 to the minus 1. So that would be C equal to 10 to the minus 4, okay? Or what I would say as 100 microfarads. So a pretty normal type of circuit, okay? So let's say I have 1 over 0.1 S plus 1 times 1 over S minus S naught. Now our goal is to find V out of T and determine what that is. So what that means we need to do is basically find the inverse Laplace transform. Okay, this is the inverse Laplace transform of V out of S. This is the same thing we did in differential equations. Okay, so let's take the inverse Laplace transform of this whole thing. To do that, we had to make use of what we called partial fraction analysis. Okay, partial fractions. So in the whole partial fraction analysis, I say, in this case, I have 1 over 0.1 S plus 1 times S minus S naught. Okay. And just remind ourselves that that is V out of S. Okay, the transform of the output. That can somehow be made equal to A1 over 0.1 S plus 1 plus A2 times S minus S naught. And remember, basically what we're saying is, how would we combine these two rational functions to equal this one here on the left? Well, remember what we would do is we would multiply by 0.1 S plus 1 and 0.1 S plus 1 on this guy. And this one would be multiplied by S minus S naught and S minus S naught, like that. Okay. So what that means when I look at this is if I just look at the numerators here, I know that 1 has to be equal to A1 times S minus S naught plus A2 times 0.1 S plus 1. All right, this is basic arithmetic stuff that really you learned in probably about the 9th grade or something. So you should, if you don't follow that, just, look at that slowly later. Okay. So our job now is to figure out, well, what is A1 and what is A2? All right, so let's start with that. All right, so I'm going to start with first A2. Okay, so to do that, I'm going to say, well, let's let S equal to negative 0.1. Or, sorry, let me say S equal to negative 1 over, all right, you know what? Let me do this slowly. All right, what value of S is going to make this equal to 0? So I can say 0.1 S plus 1 equals 0. So 0.1 S equals negative 1. So S equals negative 1 over 0.1, or in this case, negative 10. Okay, so let's do that. So I'll say let s equal negative 10. So that means that this a2 term would go away, and I would have 1 equal to a1 times minus 10 minus s naught, like that. Okay? So in this case, a1 is equal to 1 over, sorry, I'll just say it, negative 1 over 10 plus s naught. Okay? All right. Well, what about a2? Well, for that, I would say let s equal s naught. Then this term over here would go away, and I would have 1 equal to a2 times 0.1 s naught plus 1. And I'd have a2 equal to 1 over 0.1 s naught plus 1. Okay? So now I want to plug those back into the expression that I started out with up here. Okay? So I have v out of s now has to be equal to a1 over 0.1 s plus 1 plus a2 over a2 over s minus s naught. So I plug my results in there. So I have negative 1 over 10 plus s naught over 0.1 s plus 1 plus, I'm going to write this as 1 over 0.1 s naught plus 1, that number, times 1 over times s minus s naught. Okay? Now, because s naught would be a constant, okay? So let's, I mean, for sake of argument, it could be, it could be 3 plus j4, okay? Because that's just a constant, what I have is this box number here is a constant. This box number here is a constant, okay? So essentially what I have is, in each of these cases, and I guess I have it written right here, right? I have constant over some Laplace transform function of s, and a constant over some Laplace transform function of s. So this guy becomes, if I'm careful about this, let me just be careful with the one on the left here, and I'm going to say 0.1 s plus 1 over 10 a1 plus the 1 over 0.1 s naught plus 1 times 1 over s minus s naught. Okay? So this guy simply becomes, over here on this side, a1 over 0.1. So if I do now, at this point I can do the Laplace transform, or inverse Laplace transform of this expression. Alright, so if I take the inverse Laplace transform of this particular function right here, alright, what I end up with is a1 over 0.1 times e to the negative t over 10. Now for this guy, I have 1 over 0.1 s naught plus 1 times e to the s naught t. Okay? And of course this only applies for t greater than 0. Okay? So this guy here, because he's got that negative here, this is our old faithful transient response. Okay? Which we're going to kind of begin to ignore here relatively soon. And this guy is my steady state response. Now one thing I want to remember, if you go back up to the beginning of the video, we see the transfer function h of s is equal to 1 over 0.1 s plus 1, right? So if I go all the way up here, right? So this here was our h of s, okay? So if I remember that, I can see that this, I can think of the steady state part, so V out steady state, right? This guy here, I can think of as V out transient. Okay, so the decaying exponential is the transient plus V out steady state. Okay, so V out steady state looks like it is equal to the transfer function evaluated at S naught times e to the S naught t. Okay, so what that says is, in the special case that I have a complex exponential input, the steady state response is simply going to be the complex exponential that I put in times the transfer function evaluated at the complex number S naught. Okay, now that result's kind of important, and it's actually something that we already knew. But to understand that a little bit further, we need to go back and we need to kind of remember for ourselves what it is to be a complex exponential. Okay, all right, so let's think about that in the next part of the video.